Let's now look at fixing the problems in the Rutherford model and talk about some experiments and atomic models that we can use. Rutherford's atom was a powerful improvement over Thomson's. It was a nuclear atom. It demonstrated that the atom was well over 99.9% empty space and put the electrons out in that empty space. It identified the electrons as the engines of chemical change. All chemistry is electron chemistry. And it put the positive charge in the center, in the nucleus, and the negative charge on the outside. So it was an improvement over Thomson's model without losing the advantages of Thomson's model. Rutherford's atom, though, had problems. The electrons, as you can see from the image on the screen, they swung around the nucleus, and they ignored the fact that molecules have to have a definite shape. Atoms always seem to be bonded in definite configurations. And the more we went into the 20th century, more obvious that was. Whereas these electrons are constantly chasing around the nucleus. And worse, the atom was unstable according to classical electrodynamics. We'll see that accelerating charged particles lose energy. And what do you hear if you're driving a car with an AM radio and the AM radio is on and you drive under one of these high voltage lines? Most people have experienced static. It sounds it's an incoherent radio wave, and it's coming from the alternating current in the high voltage lines that you're driving under. See, Rutherford was a good physicist, and he knew that when charged particles accelerate, in this case change directions, they lose energy. In the case of the high voltage line, you lose energy by broadcasting radio waves. Now, as the electron moves around the nucleus, in order to stay outside the nucleus, if it's moving like a planet around the sun, it's accelerating towards the nucleus. It must therefore lose energy, and as it loses energy, it loses speed. It gets closer and closer to the nucleus and spirals into the nucleus in less than 10 to the negative 9th seconds. That's a nanosecond. While it collapses, we would hear or see a kind of a scream from high to low as each of the energy changes occurred. So we would see a continuous spectrum of light as the electron spiraled into the nucleus. However, we know from just experience that we don't collapse. Electrons appear to remain in orbit indefinitely. So the laws of classical electrodynamics are not holding in the vicinity of the nucleus. So what does happen? That we need to answer through experiment. We need to find out how atoms do give off light once they absorb energy. How do they release energy? Now let's investigate what kinds of light hot gases give off. If you have not yet done this experiment, what we call an emission spectrum experiment, then please stop the video and do that experiment, and then come back when you're through. Did you see a full spectrum from the hot gases as they emitted energy? You really didn't. What you saw was particular wavelengths coming off of, in this case, this looks like a helium spectrum. Our experiment tells us that as electrons lose energy, they don't lose all the energies. There's not a continuous spectrum of light coming off. They lose particular wavelengths of light. They have lines, not spectra. Now, let's review the nature of light. Light is energy transmitted by electromagnetic waves. The wavelength is the distance between the crests of the waves. You can see that here, the wavelength crest to crest. The frequency is like the time between the waves, kind of how fast the wave is moving in terms of the number of waves per second. We know that wavelength times frequency is equal to wave speed. Wavelength, symbolized by the Greek letter lambda, and frequency, we'll use an F, is equal to the speed of light. So the wavelength of light times the frequency of light equals the speed of light. So let's look at a problem. Red light of a certain kind has a wavelength of 4.00 times 10 to the negative 9th meters. What is its frequency? The speed of light is 3.0 times 10 to the 8th meters per second. You can stop the video and solve the problem and come back for the answer. If the wavelength times its frequency is equal to the speed, the frequency must be equal to the speed divided by the wavelength. That's 3.0 times 10 to the 8th meters per second divided by 4.0 times 10 to the negative 9th meters, or 7.5 times 10 to the 16th. Now meters over meters is 1, so the unit is 1 over seconds, or reciprocal seconds, which you see here as the unit. That is a very, very high frequency. You're also going to need to solve energy problems. Energy is measured in joules. The energy of a photon of light, a packet of light, is proportional to the frequency of that packet of light. Energy is equal to a constant times the frequency, and that constant is called Planck's constant. It's symbolized by an italicized letter H. H is a very, very tiny number, 6.626 times 10 to the negative 34th joule seconds. So when you multiply this by frequency, which is 1 over S, your answer of energy will be in joules. So what is the energy of a photon of 535 nanometers of light? Well, again, the energy equation and the frequency equation. So energy is equal to Planck's constant times the speed of light over the wavelength of light, because this ratio is the frequency. Now remember that 1 nanometer is 10 to the negative 9th meters. So if we plug our numbers into this equation, we get Planck's constant here. We're going to divide by the wavelength, 535 times 10 to the negative 9th meters. And then we're going to multiply by 3 times 10 to the 8th, which is, of course, the speed of light. We end up with 0.0371 when we do all of these numbers. And we, of course, take 10 to the negative 34th. We're going to add the 8 exponent on this 10. And we are going to subtract the negative 9th because we are dividing by 10 to the negative 9th. And when we do that, we come up with 3.71 times 10 to the negative 19th joules. That is the energy of a photon of 535 nanometer light. Now, what did your investigation show? It showed that hot gases and ions do not give off white light, a continuous spectrum. White light is the mixture of all wavelengths. Hot gases gave off discrete wavelengths of light. For instance, from neon, you had distinct frequencies. From hydrogen, you probably had only 2 or 3 that you actually saw. From krypton, you probably had more, but again, they were in distinct lines. Now, the mixture of colors from the emission spectrum gives the distinctive color of each emission lamp. This is the neon emission spectrum, which is from the internet. But when they mix up and you just look at the bulb itself, as you see on some neon signs, advertising signs, you see the result of mixing all of these wavelengths together. The red, obviously, and a little bit of yellow predominate, giving you a very orange spectrum. The colors are mixed to give the color that is seen by your retina. Now, what is the meaning of this? Well, we're looking at this hydrogen spectrum, and we have lines, distinct lines. Only certain energy changes then are allowed when electrons lose energy, not just anything, because we've got a line at 419 nanometers, at 434, at 486, and at 656, and in the visible spectrum, those are the only lines we see. Therefore, this represents a particular energy change, this a different energy change, and so on. Only 4 energy changes are visible here. Bohr had a good interpretation of this, and he said, well, in the vicinity of the nucleus, electrons don't obey the laws of classical electrodynamics. They don't assume just any energy, any orbit. He said electrons may orbit only at certain distances from the nucleus. These are corresponding, he said, to particular energy levels. Electrons can jump from one energy level to the next, but they may not be anywhere in between. And he calls these levels electron shells. This is a diagram of the energy levels of Bohr. And you can see the ground state here, the lowest energy level. It's kind of like a hole in the ground. And then a second state and a third state here. And electrons are normally at ground state at their lowest energy, where n, which we call a quantum number, is equal to 1. They can jump from here to there, but they can't be anywhere in between. The lowest energy state is called the ground state. Electrons can absorb energy and jump up. They can absorb energy enough to jump from the first to the second stage or second shell, and then they can drop back down, and then that's when they would release a specific discrete amount of energy as light as they fall back to ground state. This energy of light is in the ultraviolet range. It was not on the picture that you saw a little while ago. You cannot see it with your eye. But if it has gone to the third energy level and dropped to the second, this releases light in the visible range. But again, a specific line, a specific frequency, a specific energy. So each of these lines comes from zillions of energy level changes in billions of hydrogen atoms. This is a simplified Bohr picture showing the nuclear atom, nucleus, and the allowed energy levels, 1, 2, 3, 4. The energy level is also known as the first quantum number, n. We'll use that later. Bohr refined the model he got from Rutherford and explained how electrons emit light. Here's another look with the electron falling from the second to the first energy level, giving off ultraviolet light. The photon of light that is emitted depends on the energy level change. And that is not just any energy level change, it's a discrete, specific energy level change. Now, 20th century physics has refined this quantum model of the atom, and we'll look at that in another video.